Okay, so we're here today to learn how to write noble gas notation corresponding to electron configurations for neutral atoms. Okay, and the noble gas notation is a shorthand way of writing electron configurations. Okay, for periods 1 and 2, it's not really much shorter than the regular way to write electron configurations. Once we start to get up periods 4, 5, and 6, it's a much more compact and shorter way to write electron configurations. So without further ado, let's get started here. So I'm going to write the electron configuration for a neutral oxygen atom. Okay, so there we are. All right, and I'm going to draw this red squiggly line here. And to the left of that red squiggly line is the electron configuration for helium. So I'm going to write helium here. And then I'm just going to write the valence electrons for our neutral oxygen atom. All right, so this is the noble gas notation for a neutral oxygen atom. Okay, and we should always check two things in every electron configuration. Total number of electrons. Well, this helium has 2 electrons. Plus 2 more is 4, plus 4 more is 8. We should also check the number of valence electrons. 2 plus 4 is 6. Oxygen is in Roman numeral group 6, so we expect it to have 6 valence electrons, which this does. Now, we see here that the noble gas notation is not really any shorter than the regular electron configuration. But once again, oxygen's in period 2, we don't really expect it to be a whole lot shorter. Okay, so there is the noble gas notation for a neutral oxygen atom. All right, let's do a few more here. Let's take a look at a neutral, let's say aluminum atom. Aluminum atom. So we'll write 1s2, 2s2, 2p6, 3s2, 3p1. All right, and I'll draw a squiggly line here. And to the left of that line, this is the electron configuration for a neutral neon atom. So I'm going to write neon here. All right, and then to the right of that are my valence electrons for my neutral aluminum atom. All right, now let's go ahead and ask our 2 questions. Total number of electrons. I should have 13 for a neutral aluminum atom. There's 10 in neon, 12, 13. So that's good. All right, let's make that one a little darker. All right, and how about valence electrons? Well, I like to underline the highest period number containing my valence electrons. Aluminum is in Roman numeral group 3, should have 3 valence electrons. There they are. 2 plus 1 is 3. So this is good. This is the correct noble gas notation for a neutral aluminum atom. All right, and again, now we can see the noble gas notation is a little bit more compact than the regular electron configuration. Okay, let's do a neutral bromine atom. A neutral bromine atom. Okay, so bromine is atomic number 35. So 1s2, 2s2, 2p6, s2, 3p6, 4s2, 3d10, and let's see, we said bromine, so 4p5. But now I have these d electrons here. And when we have d electrons, we have to rewrite the electron configuration and move the d electrons before the valence electrons. Right now, the d electrons are splitting the valence electrons, the 4s2 and the 4p5. It's splitting. So we want to have all the valence electrons together at the end. And so let's go ahead and rewrite that. 1s2, 2s2, 6, 3s2, p6, 3d10, 4s2, 4p5. Okay, now when we do that, notice we have all the period 1 together, all the period 2 together, period 3s are all together, and all the periods 4 are together. So the electrons are now in order from lowest energy to highest energy. All right, proper order from lowest energy to highest energy. Now, that's where we're going to put our squiggly line. There it is. All right, to the left of that To the left of this squiggly line is argon. Okay, argon. And then we're just going to write what's left, 3d10 on the right-hand side of our squiggly line. 4s2, 4p5. All right, 4p5. Now, we should check total number of electrons. We should have 35 for neutral bromine. Well, argon is 18, 28, 30, 35. So that's good. That's good. How about valence electrons? We're going to underline the valence electrons, the highest period number. Bromine is a halogen in Roman numeral group 7a. Should have 7 valence electrons. There they are. 2 plus 5 is 7. All right. So again, we check total electrons and valence electrons in every electron configuration. But now we have these D block electrons. So we have 2 more questions to ask. Did I drop down a period number? Yes, I did. This is 3D, not 4D. And did I rewrite the electron configuration moving to 3D before the 4s? Yes, I did. Before the valence electrons. Yes, I did. So this is correct. This is the noble gas notation for neutral bromine atom. And you see, it is a bit shorter than the normal electron configuration is. Now, we want to, the question though is, why this, I said earlier that this was supposed to be a shorter way of writing our electron configuration. But it looks like I'm doing double duty here. I'm writing the original electron configuration, the regular way, and then I'm using that to write the noble gas notation. Okay, I'm doing twice as much work. But the whole purpose of this is that it should be shorter. It should be shorter. So how can I go directly and write the noble gas notation without having to write the original long formatted electron configuration? And the answer to that is we're going to use the periodic table to do that. Okay, so I'm going to erase this, and we're not going to write the long electron configuration anymore and draw the squiggly red line. All right? Because again, that kind of defeats the purpose. This is supposed to be a shorter way of writing electron configurations. All right, so I'm going to share a periodic table up here on the screen. Okay, so let's choose a neutral antimony atom, number 51. All right, so I should have 51 total electrons. A neutral antimony atom. Okay, now, what's the nearest inert gas? Well, that would be xenon. The only problem is xenon has too many electrons. It has 54, but we only need 51 for antimony. So the general procedure, the standard operating procedure for this is put your finger on the element of interest and go backwards to the first inert gas that you run into, which would be krypton. So again, I'm going to start at antimony, and I'm going to go backwards until I hit my first inert gas. Okay, remember, the inert or the noble gases are Roman numeral group 8A or group 18. Okay, so krypton is going to start us off. All right, so I'm going to write that on the board once I stop sharing here. But then, so, okay, I begin with krypton. Then what do? Then I'm going to go forward until I get to antimony. So at krypton, then 5s2, 4d10, not 5d10, but 4d10, got to drop down a period number for D block, and then 5p3 to brings us to antimony. So again, let's repeat that again. I start at antimony, go backwards to the first inert gas, krypton. Then I go forwards, 5s2, 4d10, 5p3 to end up where we started at, and antimony again. Okay, so I'm going to stop sharing there, and we'll get that up on the board here. So that was krypton, 5s2, 4d10, 5p3. But again, I have D block electrons splitting my valence electrons, so I'm going to rewrite this moving the valence electrons before the 5s2. So we'll rewrite it. No point in counting electrons or anything at this point until we have rewritten it. Okay, so there we go. So now let's count our electrons. All right, 36 for krypton, 46, 48, 51, which is correct for a neutral antimony atom. All right, then we should check valence electrons. Valence electrons, highest period number. We have 2 plus 3 is 5 electrons, and antimony is in Roman numeral group 5A, so we should have 5 valence electrons, and we do. But we also have these D block electrons, so we got to ask 2 further questions. Okay, did I drop down a period number for D block? Yes, I did. 4D, not 5D. And then did I rewrite the electron configuration, moving the D block before the 5s? So I have all the valence electrons together. Yes, I did. So this is correct. This is the proper noble gas notation for a neutral antimony atom, atomic number 51. Okay, so we'll do a few more here. I won't ask if there's any questions because there's nobody in the audience. All right. Let's share the screen again. Okay, so this time, why don't we let's pick molybdenum, number 42. Molybdenum, number 42. So as always, I'm going to go backwards until I encounter the first inert gas. Krypton again. Krypton again. Okay, then I'm going to go forwards until I hit molybdenum. So I'm at krypton, then 5s2, and then 4d4. Again, I'm going to, okay, just to review that again. I'm going to start at molybdenum, go backwards until I hit the first noble gas, krypton. Then I'm going to go forwards, 5s2, 4d4, until I hit molybdenum again. Okay, so I'm going to stop sharing, and we'll get that up on the board. Okay, and we have krypton, 5s2, 4d4. Now I have these D block electrons, so I have to rewrite the electron configuration. So we'll do that. Krypton, 4d4. Gotta be careful not to write 4d10. This is why we count electrons. All right, so there we go. So now we're going to count total electrons. Molybdenum is atomic number 42, should have 42 total electrons. Well, 36 for krypton, 40, 42. So we're good there. How about valence electrons? Well, every D block element has 2 valence electrons. There they are. And then since we have D block electrons, I have to ask, did I drop down a period number? Yes, 4D instead of 5D. And did I rewrite the electron configuration, moving the D block electrons? Yes, I did. So this is the proper noble gas electron configuration for a neutral molybdenum atom. For a neutral molybdenum atom. Okay, so we'll do a few more here. Okay, so let's share the screen one more time. And so let's do a cesium atom. Cesium, number 55 over here. Okay, on the left-hand, far left-hand side. So I'm going to go backwards to the first inert gas, which is xenon, number 54. The first inert gas, which is xenon. And then I'm going to go forwards until I hit my atom of interest. Well, it's the first one, cesium, number 55, which is 6s1. So again, I'm going to start at cesium, go backwards to the first inert gas, which is xenon, and then forwards, 6s1 brings me to cesium. So we'll stop sharing, and we'll get that one up on the board. So xenon, 6s1. All right, so there it is. Now, let's count total electrons. 54 for neon, then one more is 55 for a neutral cesium atom is correct. And valence electrons, there it is. Highest period number, 1 electron. Cesium is in Roman numeral group 1A, an alkaline metal, which should have 1 valence electron in the neutral cesium, which this does. Now, let's just see how much shorter this is than the old way. All right, the old way would be 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2. Am I going to have room? 4p6, 4d10, 5s2, 5p6, 6s1. All right, so let's count them up. 2, 4, 10, 12, 18, 28, 30, 36, 46, 48, and 7 more is 55. So yes, this is correct. All right, and 1 valence electron. Look how much shorter our noble gas notation is than the fully expanded electron configuration. Much, much shorter. Much, much shorter. Okay? So chemists quite often use this when they're only interested in the valence electrons, which is most of the time. They're the ones involved in chemical reactions. Okay, the inner or core electrons do not participate for the most part in chemical reactions. All right, so we'll do 1 or 2 more here. So I'm going to share the screen again. And let's go back down to one of the lower atomic numbers. All right, so let's look at, say, carbon. All right, so atomic number 6. We're going to go backwards till we hit the first noble gas, which is helium. Helium. Then we're going to go forwards until we get back to carbon. So helium, then 2s2 and 2p2 brings us back to carbon. Again, to repeat the whole procedure, we start at carbon, we go backwards, backwards, backwards until we get to the first entered gas, which is helium. All right, then we go forwards to our atom of interest, 2s2, 2p2. I'll stop sharing and we'll get that up on the board. Okay, so helium, 2s2, 2p2. Okay, and check total electrons. Carbon should have 6, 2 for helium, 4, 6. That is correct. And how about valence electrons? Carbon is in Roman numeral group 4A, so it should have 4 valence electrons. There they are. 2 plus 2 is 4. We don't have D block electrons to concern ourselves with for carbon, so this is correct. This is correct. Okay, and we'll do one last one. We'll make sure I don't get locked in. All right, we'll share the screen one more time. One last time. Okay, let's pick nickel. Nickel, number 28. So we're going to go backwards, back to the first noble gas, argon. Argon. Then we're going to go forwards until we get back to nickel. 4s2, 3d8. Again, we start at nickel, go backwards until we hit the first noble gas, argon. Then we go forwards, 4s2 and 3d8. We got to remember to drop that down a period number for D block. So this is 3d8, not 4d8. All right, so I'll stop sharing. We'll get that up on the board. So that was argon, 4s2, 3d8. We have D block electrons, so we're going to rewrite it, moving the D block electrons before the valence electrons. Okay, so we're going to check total electrons as always. 18, 20, 28, which is nickel. And how about valence electrons? Highest period number is our valence electrons. There they are. Remember, every D block element has 2 valence electrons. 2 valence electrons. Okay, and we have D block electrons, so we have two more questions to concern ourselves with. Did I drop down the period number for D block? Yes, I did. This is 3D, not 4D. And did I rewrite it, moving the D block electrons before the valence electrons? Yes, I did. Yes, I did. Okay, so that's it. That is noble gas notation corresponding to electron configurations for any of the elements on the periodic table up to atomic number 57. We're not going to concern ourselves with F block. It starts to get a little too complicated there for the level we're at. Okay, so hopefully you learned something here, how to write noble gas notation, electron configuration. And thank you for joining us, and good luck.